Hello students, welcome back once again. So we will continue with our discussion on waves. Okay, so previous class we talked about transverse and longitudinal waves, and we could distinguish between what is transverse and what is longitudinal waves, and we got different examples for both transverse and longitudinal waves. Okay. And we also try to frame wave equation, so which represent the oscillation of particles in a medium, and we could express the displacement of the particle at any point along the axis of propagation in terms of y, x and t. Okay, so we express it as sinusoidal function, and y is equal to some amplitude multiplied by sine of some phase value. Okay, so this way mathematically we could represent the wave propagating in a one-dimensional plane, and we could also explain what is the phase of a wave, what is the physical meaning of phase of a wave, and subsequently we explain phase velocity of a wave, and we define it as the velocity with which the points of constant phase, the points of constant phase of a wave moves, and we could illustrate it very beautifully, and we understood the concept of phase velocity. And today we will continue the discussion of wave with a special focus on differential equation of wave. Just like for harmonic vibrations, we could derive a differential equation for oscillating particles or vibrating particles. Similarly, we will try here to obtain a differential equation for a wave, a propagating wave. So that is a very core idea of this module. Previous class we got the expression for a wave. This is also called wave function. Okay, wave function, because it is a function which represents a propagating wave. Okay, so we will obtain the differential equation of the wave using this wave function. What we will do, we know here there are two parameters. One is x, other is time, or position and time. We will repeatedly differentiate the given function, first in terms of time t, and secondly in terms of position x. So we will look into what is the rate of change of y with respect to time, as well as the rate of change of y with respect to x. Then some comparison will be made, and that will lead us to the differential equation of wave. Okay, so let's see how this is done. For that, first we will differentiate the above equation with respect to time. When we differentiate with time partially, you can write it like this. Okay, delta y by delta t is equal to delta by delta t a sine kx minus omega t. Okay, so here differentiation is purely with respect to time, so x is not taken into account. We will not differentiate x part. So when we differentiate, what we get, we can differentiate sine kx minus omega t, so that will give us cosine kx minus omega t. And we have also to differentiate the phase part, so that is given here, delta by delta t of kx minus omega t. So when we do the differentiation of the argument part, what we will get, it as delta y by delta t is equal to, or del y by del t is equal to minus a omega cos kx minus omega t. Okay, so our first step is over. We differentiated the above equation partially with respect to time. We will once again differentiate the above equation partially with respect to time. Then what will happen? We can write del square y by del t square is equal to minus a. Okay, you have to differentiate cosine part once again, so that will lead to minus sine kx minus omega t, and when we differentiate inside the bracket, you will have an additional minus omega. So altogether what we get? We get minus a omega square sine kx minus omega t. So this is the second order differential of y with respect to time, and that we got. Now we will move on to differentiate the wave function with respect to x. First let us differentiate with respect to x partially. So you can write like this: del y by del x is equal to del by del x of a sine kx minus omega t. Again we can follow the same principle, but here differentiation is subjected to kx part only, not for the omega t part. So you see, you can write a cosine kx minus omega t into t, or ak cosine kx minus omega t. Okay, so once again you can repeat the process by differentiating once again with respect to x. That will lead us to minus ak square sine kx minus omega t. So we executed two-time differential for with respect to x as well as with respect to time, and we got two results like this: one for del square y by del t square and one for del square y by del x square. Understand? And some modification you can of course make. If you make a modification here, we get a sine kx minus omega t equal to minus 1 by omega square del square y by del t square. Similarly, second part, if you make a rearrangement, we get a sine kx minus omega t equal to minus 1 by k square del square y by del x square. Okay. Now both parts are similar, identical. You can equate it. Once you equate, what we get? Minus 1 by omega square del square y by del t square is equal to minus 1 by k square del square y by del x square. Okay. So you can make some rearrangement. What we will get is del square y by del t square is equal to omega square by k square into del square y by del x square. And already we have studied that omega upon k is equal to phase velocity. In the previous module we got this relation: omega by k is equal to vp. You can insert here, you can replace your omega by k with vp. So we will get it. Yes, del square by del t square is equal to vp square into del square by del x square. This is in fact known as the differential equation of a one-dimensional wave. Why do we call it one-dimensional? Because here wave is propagating along the x direction. So this equation is called differential equation for a one-dimensional wave. Okay, this is a standard differential equation, standard form. Just like we studied a standard form for simple harmonic addition. Similarly, here this is the standard differential form of a one-dimensional wave, a wave propagating along one dimension. Now you can say, for example, you can represent a one-dimensional wave like this. Understand? A one-dimensional wave propagating along a particular direction. Okay, then this equation is enough. But suppose our wave is something which is propagating along a surface, a two-dimensional plane, something like a water wave. Suppose you produce some wavelets on a pond, on the surface of a pond, or anything like that. So this is a two-dimensional wave. Then there will be variation of disturbance along x and y direction. X and y direction. Then your expression had to be changed. Okay. So in order to do that, in that case we have to take y as a parameter, a spatial parameter. So we can replace the height of the disturbance in terms of h. So instead of y we will use h as a function of x, y, z, t, depending on the requirement. Okay. Sometimes h may be simply a function of x, that we call a one-dimensional wave, where h represents the height of the wave at a distance x at a time instant. Understand? Suppose we are talking about a water wave, then we need a h and y. Okay, so we get a two-dimensional wave. So this is a two-dimensional wave now propagating in a plane, not along a single direction. Okay, so we have del square h by del x square, del square h by del y square. Hope this idea is clear. Of course, if you have a two-dimensional wave, then we can definitely narrate a three-dimensional wave also. Because there are so many examples for three-dimensional wave. For example, suppose you have a light source kept at some point, a single point source, for example, then the wave propagating in all the direction is an example for a three-dimensional wave. Or for that matter, you assume something like a sound source, a sound box, something kept at the center of a room, where again you can have a three-dimensional wave all around the room. Okay, that is another example. Or you can imagine about an earthquake, which can also propagate in all the directions. So these are all examples for a three-dimensional wave. In such a case, a three-dimensional wave can be represented like this. Okay, where you can see three terms are there. One is del square h by del x square, other is del square h by del y square, and we have del square h by del z square. Understand? So this way you can extend the wave from one dimensional to two dimensional to three dimensional. Okay, and a few more comments about three dimensional waves. We have already represented the three dimensional wave like this, which is required whenever we talk about a wave, a disturbance propagating all around in a 3D space. In such cases, usually this operator, an operator you can see inside the bracket as del square by del x square, del square by del y square, and del square by del square. So this is usually represented as using the capital delta. Okay, so this is actually called nabla. So in Greek alphabet, this is also called nabla square. Okay, this is also known as Laplacian. Understand? Laplacian del square. Okay, so then the above 3D equation can be briefly represented like this. You see now del square h by del t square is equal to phase velocity square into del square h. Okay, so this briefly, compactly represents a 3D wave propagating in a three-dimensional space. Okay, so this way you can narrate differential equation of a one-dimensional wave, two-dimensional wave, or a three-dimensional wave. Understand? Also, this is a beautiful illustration of, or mathematical illustration of any sort of wave. Okay, so here is a question for you to do now. We have already got the wave equation, we have already got the differential equation, both we know. Okay, so if a question is given like this, y is equal to x square plus v square t square, you have to prove that whether this is a representation of a wave or not. Okay, we are not sure that this is a wave or not. How will you prove it? You can easily prove it, because you take dou y by dou t or del y by del t, then take del square y by del t square. Similarly, you take del square x by del square y by del s square, as we did in the previous slide. Okay, you get it. You get, and if you are getting a equation of this kind, you just differentiate first one with respect to time 2 times. You just differentiate the first one with respect to x 2 times. And if you are in a position to compare like this, if you can write like this after differentiation, then you can say that the equation represents a wave. And if you are failing to represent like this, then you can say that this does not represent a wave. Understand? So this way you can proceed for all the rest of the questions. Understand? So do like that. 2-time differential with respect to time, 2-time differential with respect to x. Understand? So, and subsequently, if you get a relation like this, you can confirm that that is a wave. Otherwise, not. Okay. So this way you try to prove all the 5 questions. It's a simple program, and submit it. Okay. And if you are desirous of doing more problems on this kind of, then you have a set of problems given here. It is optional, it is up to you, but I suggest you to do it. Okay, these are standard problems. You try to prove that all these equations will give you a differential equation of this form. Okay, If it does not give you a differential equation of this form, of course that does not represent a wave. So you are suggested to do all this problem. Okay. So with these comments, let us sign off. See you back again. Thank you all.